New stuff. Oh, I hate to go to the new stuff. Because we're going back a little bit. Back to conditional probability, which was, I believe, right before the last quiz, maybe, I think. Conditional probability. And so, I want to use the Markley Oil and Collins Mining again to review conditional probabilities. And in this first column is Markley Oil, making 10,000, making 10,000. Maybe I need to review the story real quick. Remember, we came to the meeting, we have a bunch of money, we have these two investment possibilities, Markley Oil and Collins Mining. Here's the possible outcomes. Markley Oil, we can make 10,000, make 5,000, break even or lose 20,000. Collins Mining, we could either make 8,000 or lose 2,000. So combined, there were 8 possible outcomes. Here's our subjective probabilities for each of these outcomes. And we were using these probabilities that add up to 100% or 1. We were using these probabilities to answer a whole bunch of questions. What's the probability Markley Oil will make money? Okay, here's the 4 of them where Markley Oil is going to make profit. And we would add those 4 probabilities. What's the probability Collins Mining will make a profit? Okay, that's the first one, the third one, the 5th one, the 7th one. We would add those 4 probabilities and answer that question. We went from there, if you recall, a few weeks ago, and we went to talking about the union of 2 events and the intersection of 2 events. I said the union would be or, and the intersection would be and, A and D. So let me give you an example again to refresh your memory on union. What's the probability that Markley Oil makes a profit or Collins Mining makes a profit? One or the other. So I go to each one of them where at least one of them are making a profit, and I would add that probability. The first one, the second one, the third one, the 4th one, the 5th one. Not that one. Not making money, not making money. So that one doesn't fit. The 7th one, but not the 8th one. So 6 out of the 8 of them represent the union, that one or the other is making money. Real quick now, let's refresh intersection. That one and the other are both making money at the same time. That Markley Oil, what's the probability that Markley Oil makes money and Collins Mining both make money? The first one has them both making money. No. The third one has them both making money. No, 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 no. Only the first and third, 36% of the intersection that both are making money. All right, we got that. Let me write that down, matter of fact. Intersection of the 2 events, both making profit, which was 0.20 plus 0.16 equals 0.36. The reason this is important in a minute is because we're heading to where you got to realize how to figure out if 2 events are independent of each other. And to figure out if 2 events are independent of each other, the easiest way is to compare some of the calculations that we learned how to do. And one of the things you want to compare is a conditional probability. So this all led up to reviewing conditional probability. Conditional probability is where you're told that one event is given, that it happened, and asking about the probability then of the other event. Now, in the PowerPoint, the example we had was, hey everybody, let's assume Markley Oil made profit. What's the probability Collins Mining will make profit also? Did you hear that? The given was that Markley Oil makes profit. So let's figure that out. This is this right here. If Markley Oil makes a profit, what's the probability Collins Mining makes a profit? Our denominator is that given. I have to add up all the probabilities that fit the description, Markley Oil makes a profit. There's 4 of them. These top 4 have the first investment making money. So I'm going to add 0.20 plus 0.08 plus 0.16 plus 0.26. There's my denominator. That's the given. Markley Oil makes a profit. Now my numerator can only come from that given. And the question says, what's the probability, and now here's the numerator. What's the probability Collins Mining makes a profit? But there's a bunch of them Collins Mining is making a profit. There's 4 of them. Only the ones that have Markley Oil already making a profit can we choose from. So out of these 4 right here, which happen to be these top 4, only where that 8 is. does it have Collins Mining making a profit? So the numerator only has the 0.2 and the 0.16. 0.20 plus 0.16 is the numerator. So this conditional probability is the intersection over the probability of the given. If Markley Oil is profitable, there's Markley Oil being profitable, what's the probability Collins Mining was profitable out of those two? So this equals 0.36 over whatever this adds up to, which we'll look at in a minute here. There's a conditional probability. What you didn't see though is a different conditional probability. So I made up a different one. And I want you to see it, no matter what the two events being described are, you do it the same way. The given is your denominator, and the other one's your numerator. So here we go. Given, if Markley makes a profit, well, look at that. It's the same given as this one over here. So the numerator doesn't change. The denominator doesn't change. 0.20 plus 0.08 plus 0.16 plus 0.26. That has not changed at all. But then it says, what's the probability Collins doesn't make a profit? So now I can only look at these four because that was the given, but I got to pick out the ones where Collins Mining doesn't make a profit. So I'm not using, let's see, those four are these top four again. I'm not using that 20% and 60% because Collins Mining is making a profit. The question says, what's the probability out of those where Markley Oil is making a profit of Collins Mining not making a profit, which would be the 0.08 and the 0.26. 0.08 plus 0.26. There it is. There's the conditional probability for that. So you're getting it, hopefully. Someone feel they're getting it enough to talk me through. I'm just gonna make up a conditional probability off the top of my head. And I need some help, I want some help as to what numbers out of these 8 numbers would be in the denominator and the numerator. So let's go with if Collins, I'm going with Collins first. If Collins doesn't make a profit, what's the probability? What the probability that Markley, hang on. If Collins doesn't make a profit, what's the probability that Markley also doesn't, how about that, doesn't make a profit? So I got doesn't and doesn't, 2 doesn'ts. The events are different now. I always start with the denominator. The given is Collins Mining doesn't make a profit. How many up here is Collins Mining not making a profit out of 8? Anybody? 4 of them. There's 4 of them that Collins Mining is making a profit. I'm going to pick those 4 probabilities out and make it my denominator. I got 08, 0.08, 0.26, wherever the negative 2's are. 0.12, 0.06, 0.12, 0.06. There they are, there they are. Now my numerator can only come out of those 4. And the numerator represents what's the probability that Markley Oil also doesn't make a profit. I can only look at this one. Does this fit that? Markley Oil also doesn't make a profit. No. The next one's right here. Does it fit? No. This one doesn't. But then I go here, this 0.12, and sure enough, Markley Oil is not making a profit. So this is one of my numerators, 0.12. And then I go down here, and I notice that Markley Oil isn't making a profit on this one either. So that 0.06. There it is. That's the conditional probability for these 2 events. So whatever the events are, you just got to interpret it. And I want you to be careful because sometimes the grid looks like this. And you've got these types of numbers like this, you know, whatever this is, I don't know, whatever this adds up to. That was too much. 0.42, 0.41, I don't know, whatever that to add up to 100. So sometimes it looks like that with male, female, candidate A, candidate B, a contingency table like last quiz.
Doesn't Markley also not make a profit on the 0 and the...
Yeah, right here, this one. The 12%, which is the first one. But you're saying up here? No, but the given was Conley didn't make a profit first, so we can only look at these 2. Okay. All right, do we feel like we got conditional probabilities reviewed enough that we can recognize and figure them out? Because now it gets hard. Are you ready? Where do I want to start here? I want to start, oh wait. Here's our conditional probability. Which one was this? This is this one right here. Markedly oil is profitable. Given markedly oil is profitable, what's the probability Collins mining? So this is 0.36, 0.70 equals 0.5143. 0.5143. That's a 3, believe it or not. There you go. So there's that one right there. There's the example. Now the multiplication rule with conditional probability problems, and I want to make sure you recognize what that means. The second letter in a conditional probability uses a straight line. The second letter on the right is the given, is your denominator. The letter on the left is the event that's in the numerator that you're trying to find the probability of given the event on the right. So let me give you an example. Let's say this Markley Oil makes a profit, we're going to call C. Collins Mining makes, I'm sorry, we're going to call that M. Collins Mining making a profit, we're going to call C. So we just found the conditional probability here of P, C, straight line M. There is that conditional probability. Given Markley Oil is profitable, what's the probability Collins Mining is profitable? The one on the left is the one that the numerator, the one the question's about. Down here, or over here, Markley Oil makes a profit, we already made that in M, but what's the probability Collins Mining doesn't make a profit? We're going to call that C2. So now, this is the probability equals the probability of the conditional probability C2 straight line M. That Markley Oil is profitable, given the Markley Oil is profitable, what's the probability that Collins Mining is not profitable? All I did was give it a different variable. But this is how you write it. Whatever the given is on the right side of the line. So now, this one here. If Collins Mining does not make a profit, well, we made that C2. There's C2. What's the probability Markley also doesn't make a profit? We haven't given that a label yet. Let's make that M2. Now, this one's going to be, I'll put it right here, probability of M2 straight line given C2. And that equals this one. So, here's the deal. If you have a conditional probability, and the given is the right letter, which is B, and you multiply it times the probability of that itself, the probability of B, it will equal the intersection of the two events. So if you only have two pieces of this puzzle, it would be very easy to find the third piece. Let me repeat it. The intersection of two events is equal to the probability of the given event times the conditional probability of the given event under the probability of the other event. A and B can be any letters. It's just showing you that the B, the given, is being multiplied by the probability of B itself. Here's the example. The example says, okay, the probability of Markley Oil making a profit is 70%. Matter of fact, we have it right here. The 20 plus the 8 plus the 16 plus the 26. These four represent Markley Oil making a profit, 70%. The probability of the conditional probability where Markley Oil is the given, see the M on the right times M, is 5143. There's the conditional probability. So if we take that 0.5143 times that 0.7, it should equal the intersection, which is 0.36. Sure enough, 0.7 times 0.5143 equals 0.36. It proves the multiplication law rule. Sometimes called rule, sometimes called law. It's called law here. Sometimes it's called rule, same thing. But don't get it mixed up with the multiplication law for independent events. That's different. Let me repeat that. There's the multiplication law that uses conditional probability, and then we're about to learn the multiplication law for independent events. That is very different. This is not the same. This is specifically for independent events. All right, I know this is crazy. Seems hard, doesn't it? Here is proof of independent events. What is consistent about them? And what's consistent about independent events, if two events are independent, the conditional probability, whatever the numerator would be equal to the probability of that itself. Notice the B is the numerator here. It's going to equal the probability of B if the two events are independent of each other. Notice the A is the numerator here. It will be equal to the probability of A, this conditional probability, if the two events are independent of each other. If they're not independent of each other, this would not be true. These will not work. And this is one of the ways you can prove whether two events are independent or not. The other way to prove it is this, the multiplication rule for independent events. It says, and this is the most common way most people use to prove whether two events are independent of each other or not. It says if they are independent, you can take the probability of one event times the probability of the other event, and it will equal the intersection. Let's test that theory right there. The probability of Markley oil. Let me write this down. Hang on, I gotta put it where the camera can see. You ready? I'm saying that, let me write it just like you see it here. The probability of Markley oil making a profit, and what's the intersection? Upside down U? Intersection of Collins Mining making a profit equals the probability of Markley oil making a profit times the probability of Collins Mining making a profit. I can find the probability of one, multiply it times the probability of the other, and if it equals the intersection, these two events are independent. But if it doesn't equal the intersection, they're not independent. So here's the deal. Here's the intersection, right? Where both of these are making money. The first one and the third one are the only ones. 20 plus 16 is 36. So we got the 36 right here. 0.36. Now let's take the probability of Markley oil. Let's take the probability of Collins Mining making money, and let's multiply them and see if it equals 0.36. So Markley oil making money. That would be this one, this one, this one, this one. Let's add those four up. 20 plus 8 plus 16 plus 26. Help me out. 28, 38, 48, 58, 68, 70%. There's that one. So this would be 0.70 times Collins Mining making a profit. That would be that one, that one, that one, and that one. All the 8s where Collins Mining is making 8,000. 20 plus 16, 36, plus 10 makes 46, plus 2 makes 48, 0.48. If you take 0.48 times 0.70, it will not equal 0.36. And that is proof that these two events are not independent. That's where you use this multiplication law for independent events, to prove whether they're independent or not. Anybody do the math on that yet? What's 0.7? And let me get my calculator. 0.7 times 0.48 is going to be 0.336. This equals 0.336, which is not equal to 0.36, even though they're close to each other. Only about 2.5% off from each other, they're not the same. And therefore, these two events are not independent of each other. All right, I want to show you something I posted. Where is it? Right here. Which describes in detail exactly what we just talked about. It says if you open up chapter 4 PowerPoint, you'll see from slide 17 that the probability of Markley oil making a profit is 70%, which is what we used right here, 70%. You'll see then from slide 18 that probability of Collins Mining making a profit is 48%, which we did right here by adding the 20 plus the 16 plus the 10 plus the 2, 48%. And then you will see that the union between these two from slide 22, which we didn't use, happens to be 0.82. And then the intersection from slide 24, which we did use, is 0.36. So what I did is I said, are the events of Markley oil making a profit and Collins Mining making a profit independent? The answer is no, because the conditional, I did it a different way. Did I do it more than one way here? I hope I did. There's 3 different ways. Oh, here we go, both ways. Let's go to this one. No, because the intersection, which is 0.36, is not equal to the probability of Markley Oil times the probability of Collins Mining. 0.70 times 0.48 equals 0.336. It does not equal 0.36, which is the intersection. Therefore, they're not independent. Now, I proved it a different way. They're both going to be correct. You can either use the multiplication law for independent events, or you can use the definition from before. Are you ready? So, this one says, also no, they're not independent, because the conditional probability, if Markley Oil is given, it happens to be profitable, what's the probability of Collins Mining, which is 0.5143, does not equal the probability of Collins Mining by itself, which is 0.48. Those two are off from each other, so that also proves these two events are not independent. Now, I changed the events. I said, I'm going to make two events. I'm going to make M2 be Markley Oil doesn't make a profit. C2, Collins Mining doesn't make a profit. And you got to look at this as a test question. You got to say, the questions you got to say, here are the two events, that Markley Oil doesn't make a profit, Collins Mining doesn't make a profit. Are they independent of each other? Show your detailed calculations to prove your answer yes or no. Are they independent of each other? So you got to pick. Do you use the multiplication law for independent events, or do you use those other definitions where you got to use the conditional probability, whatever it may be? So I attacked this one way. I said, I think I went with intersection. Let's take a look. So I said, let's find the probability Markley Oil doesn't make money. So I said, which ones have Markley Oil? The first one not making money, 0, 0, negative 20, negative 20. These four, 10 plus 12 is 22, plus 6 is 28, 29, 30. 30%. So there's the first step. Find the probability of an event. This one, the event's called Markley Oil doesn't make a profit. Next, Collins Mining doesn't make a profit. So I had to find all the ones where it doesn't. The negative 2, the negative 2, the negative 2, negative 2. 8 plus 26, 20, 29, 30, 34, 44, 46. 46 plus 6 is 52. Does that say 52? 52%. So I found those two probabilities. Now I can multiply those two and compare them to the intersection, but I don't know the intersection. Let's take a look. Is that the way I went? No, I went with the union. Why? No, let's go with the intersection. The intersection, where both Collins Mining and Markley Oil are both not making a profit at the same time. Okay, we got both profit here. One's not making, but one is, both are, one is not. Here we go. Nope, that one here. They're both not making a profit. So we got 12%, there's one of them. And then this one, 6%. You add them together, 18% is the intersection. So now, if I take 30% times 52%, and if it doesn't equal 18%, I just proved these two events are not independent. But if they do equal 18%, I've proven they are independent. Let's see what I did. What did I do here? No. I used conditional. Let me use, no, forget conditional. Let's use this one. No, because the intersection is not equal to the probability of Markley Oil not making a profit times Collins Mining not making a profit. The intersection was 18%, and if you take 30% times 52%, you get 0.156, a little over 15.5%. That's so far off from 18%, there's no way these two events can be independent of each other. But the point I'm trying to make is, I used the exact same numbers, and all I did was change what events we're evaluating rather than independent of each other. There's Markley Oil does make a profit, there's Markley Oil doesn't make a profit. There's Collins Mining that does make a profit, Collins Mining doesn't make a profit. The events could be anything. So this is how you do it though. You've got to figure out which one is easiest for you to prove whether they are or not. If you notice, I proved it a second way. I said, I took the conditional probability, given that Markley Oil doesn't make a profit, what's the probability Collins Mining does? And that conditional probability is right here, 60%. And I compared it to the probability of Collins Mining not making a profit all by itself, which is 52%. So using that rule proves these two are not independent. Whichever way you find easiest is the way you're going to use. All right. Let me keep looking and see if there's let's make one up. You ready? This time, I'm making one up off the top of my head. Let's clear some spot for this. Let's make up two events that we haven't done already. One's gonna have to be that one of them are profitable, and the other one's gonna be that the other one's not profitable. So let's go with, we'll call M equals Markley Oil profitable. Then we're gonna go though with C2, Collins Mining is not profitable. Our question is, are these two events independent of each other? Let's go with the rule that we look for the intersection and compare it to the probability of one event times the probability of the other event. All right, so let's start with the probability of Markley Oil making a profit. These first four are the only ones that has Markley Oil making a profit. So the probability of M, whoops, come on. The probability of M equals 0.70. There's that one. The probability of C2, Collins Mining doesn't make a profit. We gotta add up the ones where Collins Mining is not making a profit. The -2, the -2, -2, -2. So 8 plus 26, again, that's 28, 29, 34, plus 12 is 44, 46, plus 6 is 52. 0.52. There's the probability of that one. I want to confirm that. Did we use that over here? No, we didn't. Okay. 0.52, the probability Collins Mining is not making a profit. Then, once I multiply these two, I want to compare it to the intersection of Collins Mining is making a profit, intersecting with C2, which is, Markley Oil making a profit, Collins Mining not making a profit. So here's the intersection. Markley Oil's making a profit, which is only these four, and at the same time, Collins Mining is not making a profit. So out of these four, that's this one and this one. 0.08, 0.26. 0.08 plus 0.26 equals 0.34. There's the intersection, 0.34 of Markley Oil making a profit, Collins Mining not making a profit at the same time. Now, what is 0.70 times 0.52?
0.364.
Excuse me. Does 0.364 equal 0.34? No, they are not independent of each other. Okay, so you just saw at least three or four different ways, different events being compared to each other to determine if they're independent or not, and showing proof that they are or are not independent. Those examples are posted, but that second example I just did it last night, so it's not on that sheet. So if there's anything you want to either take a picture of, let me make it smaller, or write down, it would be, let me make it smaller, so you get the whole thing.
Are you gonna post it?
If I can remember it. So there it is from top to bottom, whether they're independent or not, using that same grid that's not on the sheet, because I just did that one last night. Okay. Now, any questions about independent events? Go ahead, Mike.
So you see how there's the Markley and then the Collins numbers, and then there's a probability right next to it?
Yeah.
How do you get those? Or are
These
they all
probabilities are
given?
going to be given to you.
Oh, okay.
Yeah, you don't have to come up with them. If you did have to come up with them, it would be real specific as to what you guys do to come up with them. But the probabilities are given to you. And it may not be a list like this. It may be a contingent table where there's only 4 probabilities possibly. But they'll add up to 100%, whatever the probabilities are. All right, I'm gonna keep going just for the sake of if, if, one of the most important commands in Excel. Excel function if, if. It's almost like writing programs in Excel, in a way. All right, here's a quick example. If, we're looking at the data over here, C all the way to what? C keeps going all the way to C31. So C7 to C31. If C12 is greater than 100, put the word greater there, comma, if it's not, put not greater. So when you write an if statement, you put equals if, and then you put parentheses. The first part in the parentheses is a question you want Excel to evaluate. It's got to be something that it could say true or false to. In this case, I'm saying, hey, is C12 greater than 100? Yes or no? Either it's greater than, or maybe I should have put equal. It could have been equal to, and I may have blown it. Is it greater than 100? I guess if it's equal to, it wouldn't be greater than, would it? So it's looking at C12, determine. After you put a comma, you're telling Excel what you want it to do if the first thing you put is true. If the answer is true, then here's what I want you to do. Put the word greater there. That's what the quotations mean. Put the word greater in the box. Comma. After the second comma, you're telling Excel what to do if it's false. If that cell is not greater than 100, then put the words in quotations, not greater. That the quotations are telling Excel, these are the exact words I want you to place in the cell. As you notice, it put the word greater, which means if I go to C12, which is right here, that it's probably greater than 100, and sure enough, it's 112. Look at this one. This is an if statement. Again, the question's at the start, then a comma, tell Excel what to do if it's true, comma, tell Excel what to do if it's false. So if the average from C7 to C31 is less than 90, less than what? 90. Put less than. If it's false, put greater than. And sure enough, it added all these numbers. It divided by the number of numbers it had there, not excluding those letters, and it then found the average. And it determined if the average was less than 90 or not. And it said it was less than 90. So it put the words less than right there in that box. That's what it brought back. Let's try another one. If, parenthesis, C7 is greater than 25. Okay, here's the question now. Hey Excel, go look at C7. Is it greater than 25? So let's go look at C7. It's 33, so it is. So it's going to go after that first comma and do whatever we told it to do, which says, count if C7 through C31 AB. Look what I did. I used a count if for the true. I told it to do something else if the first thing's true. Okay, it's true. C7 is greater than 25. So now, go from C7 all the way to C31 and count how many cells have AB in them. And sure enough, it brought back the number 2 because it was true and it did go count how many cells had AB in it, and there were 2. If C7 was not greater than 25 though, it would have brought back the word no. So what I'm trying to show you is the true and the false in an if statement can be a whole nother statement, could be a whole nother function, Excel function, could do something completely different than just if. Matter of fact, it's very common to see in big spreadsheets if statements that have, if it's false, another if statement, and if that one's false, another if statement, until one of them are true. It's like a program question after a question after a question until it finally finds the true one. Here we go. This one. If C8, look at the arrow, left arrow, right arrow. I believe that means not equal to, is that correct? Or, right, not equal to? Does anyone agree? I can't remember, it's been in years. Is it not equal to? If C8 is not equal to 22, well, what's in C8? 23, so that's true, it's not equal to 22, so it should put not 22 there, and that's what it brought back. If it had been equal to 22, it would have brought back the word equal. Another if statement. If C29 is greater than 50, let's go to C29, let's way down here. C29, if C29 is greater than 50, then put greater than 50, but it wasn't. So it says, if it wasn't, now it's asking another if statement. Because the first one wasn't true, so it goes to tell, Excel jumps past the first comma to the second comma, and looks to see what to do. And the second comma says, okay, if C29 then is less than 30. C29 is not less than 30. So we got another false. If it were true, it would say, oh, it's less than 30. So it didn't say it's greater than 50. It didn't say it's less than 30. So now it's going to the false. This number must be between 30 and 50, and that's why you see the words there, between 30 and 50. it brought back. But the point of this example is you seeing an if statement, and false led to another if statement, where false then led to a conclusion that the number must be between these other two numbers. Go ahead.
So, this is on the homework, correct?
If is not on the homework.
It's not, cause I was gonna say, how would it be asked?
Yeah, this is not on the homework. This isn't, but it's such an important if. It could be on your quiz, even though I don't think I've asked a question in the past about if on the quiz, but it is one of the most used Excel functions. You're heading to where you get to operations management, and when you get to management science, I can't remember if management science is required or not, but a lot of you will end up taking it. You're gonna learn how to do what's called simulation, business simulation using Excel. And in Excel simulation, there are hundreds of these if statements in a simulation. And what a simulation does, it is saying, hey, we're thinking about expanding our business into golf bags. Well, we want to know what the cost of materials for these golf bags are going to be, what the cost of labor is going to be, but we weren't able to narrow it down to an exact number, but we've got a range, and we're able to put probabilities to these ranges. Well, a simulation will simulate if material cost a lot and sales were not good. It will simulate if sales were good and material was cheap. It will simulate all the different possibilities that could happen because of the unknowns, that you're not sure exactly what labor will cost, you're not sure exactly what material will cost. Here's what could happen. And then this simulation will be able to tell you the probability of you making a profit if you go into this expansion of business, or losing money. This is so commonly used in big business to make good decisions when it comes to things that we don't know exactly everything that's going to happen. And this simulation has a ton of if statements like these. So it's taking everything into consideration. So then you have a row that simulates, and at the far right of the row, it will tell you if you go into this project or not, whether you're gonna make a profit or not. Then you copy and paste that whole first row simulation 999 rows below it, and you simulate 1,000 times. And all these if statements and randomness are gonna use different numbers every time. And you have 1,000 different possibilities. Labor cost was high, material cost was low, sales were good. Sales were bad, material cost was low, labor cost was high. You'll have every possibility in looking at whether you can make money or not. And then you take that 1,000 and you have it count how many out of the 1,000 you're gonna lose money, how many out of the 1,000 you're gonna make money, and that's how you determine your probability of making or losing money. And we used to say, I worked for very conservative companies, and we used to say, if that simulation isn't telling us that there's better, that it's less than 8%, less than 7%, and sometimes 5% chance of losing money, we're not going forward. Let me repeat that. That means there had to have been a 95% chance that we're gonna make money for us to say, let's do this. Let's spend $3 million and go forward buying this machine and getting all these initial materials and getting the people necessary to build this new item. That's how these kind of multi-million-dollar decisions are made through simulation. All right, that's all I got. For the last thing I want to mention before we go though,